Hey everyone, on behalf of Forge College, welcome to today's Explainer. I am super excited to be your host as we tackle something absolutely crucial for Web3 adoption. Okay, let's just dive right into it. If there's one universal pain point we all know in Web3, it's paying gas fees. Imagine walking into a grocery store, picking up a free sample, and the store charges you a network fee just to open your hand. It's ridiculous, right? Well, today we're taking a massive step in our capstone module. As a reminder, we're deep into implementing ERC patterns on Solana, part of our broader journey from EVM to SVM. And today's mission? We're designing and implementing a gasless transaction flow on Solana. We want to build an incredibly smooth UX where we totally separate the user's intent from the actual fee payment.
Here is our engineering blueprint for today. We'll start with the gasless UX dream, then meet the cast of characters making it happen. From there, we'll hit the step-by-step assembly flow, look at program-side verification checks, and then stress test the whole system with replay protection. Finally, we'll wrap up by looking ahead to session keys.
All right, Section 1, the gasless UX dream, removing friction from the blockchain. So, here's the core problem we're trying to solve. Users absolutely hate paying transaction fees just to interact with smart contracts. It's easily the biggest roadblock to mass adoption. Now think back to our previous lesson where we successfully built a Solana Vault program with deposit and withdraw instructions. The challenge we're facing now is, how do we trigger a deposit in that existing vault without making the user foot the bill in Lamports? How do we let them interact for free while still keeping the network secure and, keeping the validators happy?
Moving on to Section 2, meet the gasless cast. Who does what?
What's really fascinating here is how we divide up the labor. To actually pull off this gasless magic, we have three main moving parts. First up, the user. Honestly, their only job is to sign an off-chain message that basically says, yep, I want to deposit my tokens. And the best part? They pay zero fees. Second, we have the relayer. You can kind of think of the relayer as the generous sugar daddy of our transaction. They take that user's signed intent, build out the full transaction, set themselves as the fee payer, sign it, and submit it. They're the ones picking up the tab. And finally, our vault program. It acts as the ultimate authority, verifying the signature and executing the deposit without paying or receiving any fees itself.
But wait, there's a pretty major catch here. If a user signs a message once, what's to stop some malicious actor from copying that exact same signed message and just submitting it over and over again? Well, this brings us to a vital piece of Solana architecture called the durable nonce. A durable nonce is an on-chain account that gives us a unique, replay-protected block hash. The relayer uses this specific block hash for the sponsor transaction. Once that transaction actually goes through, the nonce is either consumed or advanced. That means that exact transaction literally cannot be submitted a second time. It is our ultimate shield against replay attacks.
Okay, Section 3, step-by-step assembly flow, wiring the client-side transaction. Let's roll up our sleeves and look at the actual TypeScript helper logic we need to construct this. We've got an exact 5-step chronological process to piece together our client-side sponsor transaction. Step 1, the user signs a deterministic message off-chain. Step 2, we create an ed 25519 verify instruction that holds that signature. Step 3, we compose the actual vault deposit instruction just like we did back in lesson 2. Step 4, we fetch the durable nonce to get our replay-protected block hash. And finally, Step 5. The relayer sets themselves as the fee payer, signs the transaction, and blasts it out to the network. Let's zoom in on that very first step for a second, because it is absolutely foundational. It brilliantly illustrates how we separate the intent from the execution. You see, the user isn't signing a full, raw Solana transaction. They are only signing a highly deterministic set of bytes. This message format has to be exact. It includes the action, the vault public key, the amount, and that specific nonce. You have to serialize this consistently, kind of like using JSON stringify on a canonical object, and then the user signs those exact bytes with their ed 25519 key pair. Now, I want to pause here and issue a very bold warning. Serialization mismatches are the most common source of failures. I am literally not kidding when I say that getting this wrong is the #1 cause of developer headaches, late-night debugging sessions, and thrown keyboards. If the user signs a byte sequence that is even one single character different from what the on-chain program checks, the signature verification is going to fail. Period. Always, always print your serialized message on both the client side and the program logs and compare them byte for byte if you ever run into trouble. All right, let's look at how this builds into the transaction itself. Instruction ordering is incredibly strict here.
The ED2559 verify instruction must come before the vault deposit instruction. Why? Because the Solana runtime needs to perform that heavy mathematical signature verification first. If the signature is invalid, the transaction just halts immediately. That saves compute resources and ensures our vault logic only ever runs for fully 100% authenticated intents.
Moving right along to Section 4, program-side verification checks, enforcing the rules on-chain. So we've built the transaction on the client side, but now our vault program needs to act as the bouncer at the door. It has to rigorously enforce the rules. First, it requires that an ED25519 verify instruction is actually present in the transaction. Second, it must parse that instruction's data super carefully to make sure no one is spoofing the intent. Third, it confirms that the off-chain signed message perfectly matches the on-chain deposit arguments being passed. And fourth, it must consume or advance the durable nonce so that this specific signed intent can never, ever be used again. If all those checks pass, the bouncer unclips the velvet rope and the vault state updates. While you're testing this out, you might actually run into a pretty common snack. Are you seeing a block hash not found error? Seriously, don't panic. Just take a deep breath. This usually just means there's a mismatch with your durable nonce. Confirm you actually fetch the current nonce value correctly and make sure your relayer is properly advancing or consuming it after submission. Check your account metadata. Did you pass the nonce account as writable? Fix that little detail, try again, and I promise you'll be right back on track. Section 5. Testing and replay protection. Stress testing the machine. You know, no engineering blueprint is ever truly complete until we try throwing a wrench in the gears. In our integration tests, we need to prove our protections actually work. Think of a scenario where everything goes right, a successful sponsor deposit. The relayer submits the transaction, it confirms, and the user's vault token balance increases perfectly, exactly like we built back in Lesson 2. But then we simulate an attack, a replay rejected scenario. We try to submit that exact same signed message a second time. And beautifully, it fails with a replay error, and the vault balance remains completely untouched. Our durable nonce works exactly as intended. We also have a third critical test, the invalid signature rejection. What if someone tries to intercept the message and maliciously change the deposit amount from, say, 10 tokens to 10,000 tokens? Because they change the payload without having the user's private key to re-sign it, the ED25519 signature verification is going to fail instantly. Any tampering with the user's message is immediately blocked by our program. And finally, Section 6. Next steps, session keys, looking ahead in the capstone. We've successfully completed the testing phase, so let's take a step back and look at what we've actually achieved here. Look at the artifacts you've just built for your repository. You now have a working sponsor helper module, a functional relayer script, a rock-solid message format specification, and a suite of passing integration tests. You should be incredibly proud of this. These aren't just throwaway, one-off scripts. They are the exact, perfect building blocks we're going to reuse and refactor in our upcoming lesson on session keys.
Which leaves us with a really provocative thought to wrap up today's explainer. You now know how to let a relayer pay for a user's single transaction. But how will you adapt this relayer pattern to issue constrained, ephemeral session keys that automate hundreds of transactions without the user ever clicking approve again? That is exactly what we're going to tackle next as we continue our transition from EVM to SVM. I really want to thank you for joining me today. Remember, to dive deeper into this subject and explore a wealth of other incredible Web3 topics, head over to forge.college. Keep building, keep experimenting, and I'll see you in the next explainer.